I'm Matt from SEEQ, and we're building solutions to scale quantum computers energy efficiently. So that means for us kind of four core principles that I'm going to talk through in this brief section. So firstly, we believe that quantum control should be on chip. And then ultimately, we also believe that quantum computing should be integrated as seamlessly as possible with all other compute technologies to create a heterogeneous platform to run algorithms. We also recognize that any unique system needs a unique platform in order to run it, and that needs to be as open and as accessible as possible to any user. And for us, most excitingly, the systems we're developing are ultimately compatible with any kind of quantum computing system. So I'm going to talk a little bit about how that operates in here. So firstly, what are we doing to build a quantum computing system on a chip, and what does that mean? Well, you've seen a lot of boxes today that are at room temperature controlling qubits. In our case, all of our control and readout for qubits is on chip, integrated with qubits. And we could do that here. We've got this is a picture of our chip for a SEEQ Orange, which we're releasing this year at the end of the year. And here we've got all of the control and readout you need for a set of qubits integrated with those qubits. And we can do that because we're controlling qubits fundamentally differently. So today, in order to control qubits, at least superconducting qubits and spin qubits, you need RF drive. And what that means is you send RF pulses to your qubits, and that does the kind of high fidelity qubit control. And in order to achieve ultra high fidelities, you need to have very precisely shaped qubit pulses and very precisely timed qubit pulses. And what this ends up with is you need 14-bit AWGs in order to actually build these pulses with high fidelity. In our case, we actually just directly digitally control our qubits using a technology called single flux quantum logic. And this is based on superconducting circuits that can be clocked incredibly fast. So we clock our circuits in hundreds of gigahertz. And because they are superconducting and because they can be clocked so fast, we literally can just use individual delta pulses of very precise energy. It's always fixed by the flux quanta, and send those to our qubits. And because we can precisely time them, we can step the qubit along the block sphere and do any arbitrary rotation with very high fidelity. And in doing so, we can get away with something more like a 7-bit circuit to do all control and readout of a qubit. So ultimately, because we can do superconducting digital control, we end up with a system that's orders of magnitude lower heat dissipation than the equivalent RF electronics. And because of that, that allows us to integrate it on chip with qubits in a way that actually maintains the quality of the qubits, which is critical to scaling. And then because we're on chip, now we can do some really cool stuff to lower the I/O overhead, like multiplexing. We can do digital readout on chip, digitization, and all of that can be paired into a single thing to be able to do on-chip error correction and detection. So yeah, some really cool stuff. And then ultimately, once you've got a chip-based architecture, now you can integrate with other digital chips very efficiently. So some of you may have seen our announcement with NVIDIA early last week, where we talked about how we're doing the first chip-to-chip integration of our QPUs with NVIDIA's GPUs. And we're doing that because ultimately the future of quantum computing, we've seen a lot of this in the talk today, needs to be in the data center. So this is where users are going to want to access heterogeneous computing, CPUs, GPUs, and quantum. And NVIDIA are making incredible strides into making their GPUs accessible. So by partnering with them, we can kind of leapfrog of our technology to support those kind of systems. And so, as I said, we're developing the industry first kind of chip-to-chip integration. And because we're chip to chip and because we're digital, we can do this with incredibly low latencies and very high bandwidth. And actually, one of the challenges of scaling analog technologies is the bandwidth needed to run qubits is enormous, terabits per second. But by being digital and digitizing on the chip, you can bring that down massively. And also, when we talk about latencies, we talk about nanosecond latencies, not microsecond latencies. And all of that delivers ultimately heterogeneous compute for some pretty cool applications. Now, the next thing is all of this needs some software to run it. And we've built from the ground up our SEEQ platform. Now, this runs our full stack quantum computing reference systems, but it also is entirely modular, so anyone can bring it into their own platforms to be able to take full advantage of our chips. So this is an exciting tool to ultimately make our chips accessible. And the reason we want to do that is because our chips are compatible with any quantum computing system. And so if you're in superconducting ion traps, superconducting or spin qubits, you can actually take full advantage of our control systems and readout systems. But if you were even in modalities like ion traps or photonic systems, you can take full advantage of our readout, on-chip readout. And we see this is ultimately critical to get to real-time decoding and error correction. And this is not just real-time, outside of the fridge. This is real-time integrated on-chip with the qubits and co-processing there and there. So ultimately, this is building a fully integrated quantum computing system, which we think is the only way to really scale up in the industry. So yeah, with that, I'll say thank you.